Fascinating question that I'd always wondered is there a surface with domain of R2 where the x and the y can be any real numbers without restriction that produce at least one trace of an ellipse, one trace of a parabola, and one trace of a hyperbola? Now, if you look through the quadratic surfaces in this section, there are some that have an ellipse for some cross sections or traces, and parabolas for others. And then other conic sections might have a parabola for one trace and a hyperbola for the other. But we don't get any that have all three existing as a trace. I was thinking it was still on pen mode, but it seems to always default to erase. All right, so there is a nice, elegant function here, and I'm going to produce a function that not only produces each of these traces, the ellipse, the parabola, and the hyperbola, but it's going to have z equals -1 is going to produce a hyperbola. Z equals 0 is going to produce a parabola. And z equals 1 is going to produce an ellipse. And here's that function that I came up with. Z equals 6 times the quantity y minus x squared over 2x or 2y squared plus x squared plus 3. Now there's a lot of functions that you can come up kind of in this vein here that could work in a similar way. All right, so let's verify these. For z equals -1, let's get a hyperbola. We take 6y minus 6x squared over 2y squared plus x squared plus 3 equals -1. Okay, and divide that by 1. Let's cross multiply. We will have a 6y minus a 6x squared equals the negative of 2y squared minus x squared minus 3. And we'll go ahead and bring everything but the -3 over the left-hand side with a plus 2y squared plus an x squared plus a 2y squared plus an x squared. And we're going to have a 2y squared plus a 6y minus a 5x squared equals a -3. Which, if we want to be really thorough here, we can even make it 2 times y squared plus 3y minus x squared over 1/5 equals -3. All right, by completing the square, we'll get 2y squared plus 3y. All right, we're going to have to add the coefficient of y's half squared. 3 halves quantity squared is 9/4. And then since I added a 9 halves is really added to the left-hand side, I'm going to add a default to do erase again, plus 9 halves. Okay, so we're going to have a 2 times the quantity y plus 3 halves quantity squared minus x squared over 1/5 equals, and then let's see, -3, -6 over 2 plus 9 over 2, that's going to be a 3 halves. And we'll multiply both sides by 2/3. The parentheses will go all the way across there, like that. All right, so we've got ourselves a 4/3 y plus 3 halves quantity squared minus a 2x squared over 3/5 is equal to 1. And this will be a y plus 3 halves quantity squared over 3/4 minus an x squared. Let's see, when you multiply by 2, you divide by 1/2. Let's see, 2 over 3/5 is 2 times 5/3, which is 10/3. And then you're going to put a reciprocal of that, put a 3/10 on the bottom, equals 1. So formally, here's the hyperbola at the trace z equals -1. Although from this point, we could actually make our conclusion here that the x squared term is negative and the y squared term is positive. What this verifies is that you don't have some degenerate condition where after all the algebra you'll find out, like, let's suppose we had completed the square and wound up with something like x squared minus y squared equals 0. That's no longer hyperbola. It's a union of two intersecting lines, which is technically not a hyperbola. So this algebra, especially here, the key step there was that the 9/2 was not equal to -3. And that really helped us get some non-zero to get a hyperbola and not a union of two intersecting lines. Okay, that algebra was kind of tedious. Z equals 0 is not that bad because we completely wipe out the denominator. If we've got 6 times y minus x squared over 2y squared plus x squared plus 3 equals 0, then all we have to set is the numerator equal to 0. And that's just 6 times y minus x squared is equal to 0, or dividing both sides by 6, we just get y equals x squared. And that's a parabola. So z equals 0 goes really quickly. All right, what about z equals 1? Is it as tedious algebra as the z equals -1 case? Well, we would have 6y minus 6x squared over 2y squared plus x squared plus 3 equal to 1. So we cross multiply again. 6y minus 6x squared is 2y squared plus x squared plus 3. And this time we're going to take the minus 6y and the plus 6x squared over to this side. Minus 6y plus 6x squared on this side. So 0 equals 2y squared minus 6y plus 7x squared plus 3. All right, let's go ahead and bring a minus 3 over to the left-hand side, minus 3. Then we've got a 2 times this y squared minus 3y again. And then we've got an x squared over a 7th. Okay, now to complete the square, just like the last time, math works out the same. We're going to be adding a -3 over 2 y squared is going to be positive 9/4, so it's still going to be y squared minus 3y plus a 9/4 plus x squared over a 7th. Okay, now we basically added 9/2 to the right-hand side, so we've got to add 9/2 over here. So when we do that, we get a -3 plus 9/2, and a 2 times a quantity y minus 3/2 quantity squared plus x squared over a 7th. Okay, and this again will be a 3/2, and we'll have a 2 y minus 3/2 quantity squared plus x squared over a 7th. Multiply both sides by 2/3. And we'll wind up with 1 equals 4/3 y minus 3/2 quantity squared plus 2x squared over 3/7. And if we take 2 over 3/7, that's going to be 2 times 7/3, which is 14/3 if we put it on the top. But if we throw it into the denominator, we'll have a 3/14 on the bottom. So it's going to be 1 is y minus 3/2 quantity squared over 3/4 plus x squared over 3/14. And this is indeed an ellipse. And I used the computer algebra system Maple to sketch a graph of this. And the z equals -1 trace. Let me use the orange marker here on the z equals -1 for the hyperbola. Would go something about like that. That would be about where the z equals -1 trace would be. This part looks shorter just because the perspective of the way this thing, we're kind of looking like from the top of the hill, and we're kind of looking downhill, so we don't get the best view going down, but we get the view going up on the other side pretty well. I'm going to use red for the z equals 0 case for the parabola. That's going to be roughly about there. You can see the parabola. And to distinguish from the blues and the greens, I'm going to go pink on the ellipse. And z equals 1 is going to be roughly about there. So this is an interesting curve here with domain all real numbers, that at z equals -1, we got a hyperbola trace. Z equals 0, we've got a parabola trace. And z equals 1, we've got an ellipse trace. So a fascinating little curve there. And in general, if you wanted to have the traces kind of work out in different ways, I mean, generally speaking, you take a summation of a sub ij's, x to the I, y to the j, over a summation of like b sub ij's, x sub I, y, j, and you just kind of fiddle with numbers where the i's, the I plus j is allowed to be no bigger than 2 in this summation. Actually, in both summations, you're not allowed for the I plus j's to exceed 2. Otherwise, you're not going to get a quadric surface anymore. When you set z equal to any real number, it would be a kind of a cubic type of curve.